Let's see what we have next. This fourth one. Here it is given that the complex number x minus iy equals the square root of a minus ib divided by c minus id. From this we have to prove that the square of x square plus y square equals a square plus b square divided by c square plus d square. So let's see the solution. So we of course start the solution with the given equation, and then we take squares on both sides. So the left hand side would be x minus iy whole square, and from the right hand side the square root will vanish. So we will be left with a minus ib divided by c minus id. And then what we do, on both sides of this equation we take absolute value. Okay. And then in the next step, in place of the absolute value of square, you can write square of absolute value. What exactly are we using here? The relation that the absolute value of the product of two complex numbers is equal to the product of their absolute values. Exactly how is that being used here? You see, you can write x minus iy square as x minus iy times x minus iy, whose absolute value you are considering. So that can be written as the absolute value of x minus iy times the absolute value of x minus iy, or in other words, the square of the absolute value of x minus iy. And what did we do on this side? You know that one of the properties of absolute value is that if you have a ratio of two complex numbers, z1 divided by z2, and you are taking their absolute value, then it is equal to the absolute value of z1 divided by the absolute value of z2. Alright. Now what is this? The square of the absolute value of the complex number x minus iy. Actually it is x square plus minus y square, but that becomes y square. And because you have squared, there is that you don't have that square root. Okay, so it has vanished. Here, however, we do not have squares, but simply absolute value. That is why we have square root of a square plus, ideally you should write minus b square, but that ultimately becomes b square, so I just wrote b square. Similarly, the denominator is square root of c square plus b square. And then once more you take square on both sides. That finally gives you this equality. So that's how it is proved. In this next one, fifth one, we have two complex numbers and we have to express each one of them into the polar form, that is convert them into polar form. The first one is 1 plus 7i divided by square of 2 minus I, and the second one is 1 plus 3i divided by 1 minus 2i. So let's see. So we take the first one first, and it is 1 plus 7i divided by 2 minus I square. Note that we may have a tendency to immediately expand the square in the denominator. Please don't do that, because it will unnecessarily increase the number of steps. Your main aim is to make the denominator a real number. So what you do instead, you multiply and divide by the square of the conjugate of 2 minus I, because you have square of 2 minus I, that is why. And then what advantage does that give you? It gives you this. Okay, without expanding squares, you can take the square on this product entirely, 2 minus I times 2 plus I, and this becomes 2 square minus I square. Minus I square is plus 1 and 2 square is 4, 4 plus 1 is 5, so you have 5 square. So that way you have 25 as the denominator, which is a real number. What is happening in the numerator? Here, however, you have to expand square. So if you expand this square, you are getting what? 2 square, which is 4, plus 2 times I, which is 4i plus I square. I square is minus 1. So 4 minus 1 is 3. So that way you get 3 plus 4i, and then you do this multiplication. So if you do that, what are you going to get? 3. 1 times 3 is 3. And 7i times 4i is 28i square. So that's why minus 28. And what about the terms having I? 7 times 3 is 21. And 4 times 1 is 4. So let's continue the calculation. So this becomes minus 25, because 3 minus 28 is minus 25, and 4i plus 21 is 21i is 25i. You see that very nicely 25 is vanishing and you are left with minus 1 plus I. So that is actually really how the complex number looks in its standard form. And now we do the usual procedure. Let r be the modulus and theta be an argument of this complex number. Then you know how these quantities are related to the real and imaginary parts like this. R cos theta equals the real part and R sin theta equals the imaginary part of this complex number. And now we need to figure out what R and theta are. To find the value of R, there are two ways. Either you square and add both these equations, that will give you R, or you just straight away calculate R from what it is, that it's the modulus of the complex number. So you apply the definition of modulus. So you take the square root of sum of the squares of the real part and imaginary part. The real part is -1 and the imaginary part is 1. So that way you get the value of R to be square root of 2. And then you use the value of R back in these two equations. So you have root 2 cos theta equals -1 and root 2 sin theta equals 1, or from which you get cos theta and sin theta to be these values. Now how do you figure out theta? Again, recall what you did when solving trigonometric equations. You guess one theta and from that you get all thetas. Okay. Here, however, only one theta is enough for us because we need the polar form, not all the arguments. So you recall what we did. You first ignore the signs. Here you have a minus sign, ignore it. And you have the value 1 over root 2. So what familiar angle theta gives you this value 1 over root 2 for cos or sine? That is pi divided by 4. However, if you simply take theta equal to pi over 4, you won't get cos theta equal to -1 over root 2, you will get cos theta equal to 1 over root 2. So your cosine is negative and sine is positive. Cosine is negative and sine is positive. That means the terminal ray of your angle should lie in the second quadrant. So you make this guess that okay, the value pi over 4 will get me the numerical thing, that 1 over root 2. But I need my angle in the second quadrant, so why don't I subtract pi over 4 from pi? Pi is this. So that way I will be in the second quadrant, but then of course you have to show that actually for this value of theta you really get these things. That part you do, and you will see that yes, that is true, and that is why this is one value of theta that we can use. So now we can write our final result. So the given complex number has this polar form: modulus times cosine of argument plus I times sine of argument, and that's it. The second one, what was it? 1 plus 3i divided by 1 minus 2i. So I ask you to do that on your own. So first you have to simplify the complex number, express it in the standard form a plus ib, and you will see that you are getting exactly the same number, -1 plus I. So for that second one also, this will be the polar form. And with that, let me just end this video. There are other miscellaneous exercises that we will do. We will solve them in the next video, next week. So see you next week with those things, further things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.